started the topic of minimum mean squared error estimation. It's an estimation technique. It's not the only one. There are so many estimation techniques, but it's like a conceptually fundamental one. And the idea here is that we have basically n plus k random variables. So we have those x's and those y's. And vector y, composed of y1 up to yk, is the vector of observations or measurements. So we do experiments, we collect data, and then we know those guys. And from y, we want to make guesses regarding the components of vector x. And so what we will do is that we will build estimators. So estimators will be functions applied to the observations, and each function will spit out an estimate for the respective x. So G1 will take the observations y1 up to yk, and then it will give us an estimate for x1. G2 will take y1 to yk, our measurements, and then it will give us an estimate for x2, and so forth. Okay, and so now the question becomes, how can we design those functions in a meaningful way? As I said, there are like lots of techniques, and you can like take one whole semester, or actually two whole semester courses on estimation techniques. But MMSE is like this simple idea that we will obtain the functions g by minimizing the mean squared error. Okay, and so what we do is that we compose the error, and so the error will be a vector. Okay, the error vector will have components, and the ith component will be xi. So this is one of the guys to be estimated, and then minus its estimate. And what is the estimate? It's some function gi applied to the measurements or observations big Y1, big Y2 till big Yk. Okay, so this is basically the error in the estimation of xi. And what we will do is that we will square this error. Okay, so we will square the errors y1, yk. So we'll take the square. Okay. And then what we do is that we apply expectation. Since those guys are known, they are the measurements or observations, then we are basically conditioning on y. And this will be the mean. Okay, mean squared error. Mean means that you apply expectation given y, given the observations, and we sum over all the components, I from 1 to big N. Okay, so this is the function to be minimized. And the solution is basically, here we will assume that, you know, every function or everything here has a finite second moment. The solution will be the expected value of vector x given y. So this is the solution. Again, the proof is in the notes. In other words, that our basically vector of estimates, its first component will be the expected value of x1 given the y's. Its second component will be expected value x2 given the y's, and so forth. And so basically, like if your random variables are jointly continuous, then this expectation here means that it's an expected value for x1, right? It's an expected value for x1, but it is conditional, so you do not use the marginal distribution of x1. In fact, you use the conditional distribution of x1 given big Y1, big Y2 up to Yk. Okay, so this is this conditional expectation. Okay, and the conditional PDF itself, you know, if you know the joint PDF of vector x, if you know the conditional PDF of vector x given vector y, then basically you can obtain this conditional by the same trick, the same old trick, by integrating over the other x's, so that you end up with the conditional PDF of x1 given the y's. And the joint conditional is something that you obtain by definition. It's basically the joint divided by basically the joint of the y's. In the numerator, we have the joint PDF of the x's and the y's, and in the denominator, we have the joint PDF of the y's. Okay, so the most important thing here is this thing, that basically to minimize to minimize the mean squared error, basically we use the conditional expectation. And now what will be the minimum mean squared error? And typically when we report this result, we do averaging over y, averaging over the observations or the measurements. So this will be, so basically this is the mean squared error given y. This is x. Now the estimators will be the conditional expectation of the x's given the y's. And so this is the MSE given particular realization of vector y, and then the minimum mean squared error averaged over the y's, we will do expectation with respect to y. And this again can be shown, the derivation is in the notes, that is, this is the expectation with respect to y of the trace of Cxx given y. So Cxx we know from before, variance matrix of vector x. Cxx given y is the conditional covariance matrix of x given y. Okay, so what is this thing exactly? So Cxx, just as a reminder, what is Cxx? Cxx is basically a matrix like you take vector x minus its mean vector, and then you multiply by the transpose. So you have the expectation of the outer product, which is a way of saying that basically element LV in this matrix is the covariance of XL and XV, which is the expectation of XL minus its mean value and XV minus its mean value. Okay, so this is the covariance matrix. Again, if you have a random vector, you can take each two random variables inside the random vector and compute their covariance. And the covariance of the random variable with itself is its variance. And then you can basically put these in a matrix. And this will be the covariance matrix. But here you are doing everything using basically the distribution of x. But this is Cxx given y, which means that whenever you need a distribution for your computation, use the conditional distribution of x given y. Okay, so basically element LV inside this matrix, it's a covariance. Okay, so it is expectation of the product of two things, but you condition on the y's from y1 to yk, and now from each x you subtract not the mean value of the respective x, but you subtract the conditional expectation. Okay, so here the conditional expectation of XL given the observations, and here the conditional expectation of XV given the observations. So this will be the covariance matrix. So if you find the minimum MSE average over y, again, you do basically find it's a trace, and so the trace is the sum of the elements on the main diagonal or the sum of the eigenvalues of the matrix, and then you end up with things that depend on y, right? Because like each element here you condition on the y's, so you end up with a matrix in which each element depends on basically y1, y2 up to yk, so you take expectation with respect to y. Now let's basically look at the simple case. What if basically we have big N is equal to big K is equal to 1? So we have just one random variable big X and one random variable big Y. In that case, this minimum MSE averaged over Y will be given by the variance of X given Y, and then you average over Y. And then from the law of total variance, which we did in the previous lecture, this will be the variance of X, and then you subtract the variance of Y of expectation X given Y. Now, of course, if x and y are independent, then the expectation of x given y, right? So if your stuff is continuous, expectation of x given y is x, and then you use the basically the conditional distribution. But if x and y are independent, then this guy here is equal to fx of x if x and y are independent, and you end up that the conditional distribution of x given y is just the expectation of x itself. Okay, so the conditional expectation of x given y is the expectation of x itself. Okay, which means that so this is like the intuitive meaning of independence we talked about earlier in the course. Yeah, so basically the idea is that if y and x are independent, and then you observe y, and now you want to find your best guess, your best estimate for x given y, then in that case your estimate does not really depend on y. Your estimate is just the mean value of x. And again, here in best sense means in that the sense in which the mean squared error is minimized, okay, because you can design estimators using other optimality criteria, right? So here the result is it confirms basically the intuitive meaning of independence, which means that if x and y are independent, it means that y tells you nothing about x and x tells you nothing about y. And so if you use the y's to estimate the x's, and if they happen to be independent, then again, like you go and compute the expected value of x given y, which is the general formula. But if they are independent, this basically becomes just the expected value of x. And so the observations are irrelevant. Regardless of what observations you get vector y can be anything according to the distribution of vector y. But in all cases, your estimate for x will be just the expected value of x. Again, this confirms that that independence means this. Independence means that go and observe y. Guess what? Nothing. You gain no information about x. Okay, so this is again like sort of a confirmation of the intuitive notion of independence. Now, what if we take the expectation of x minus x hat? No, it's not the MMSE. The idea here is that you have a problem in your choice of the observations. Okay, so so if you want to estimate x, go and observe random variables that are dependent on x. Okay, so if you go and observe random variables that are basically independent of x, then then you gain nothing. Basically these will be useless for your purposes. Okay, so it means that if our estimator should act on measurements or observations, these observations must be related. They must somehow be in fact, like the extreme case, if you can observe the x's directly, right? So again, like one thing, why actually we don't observe the x's? So sometimes it's a practical constraint, or basically the y's may be the x's, but there is always measurement error. Okay, so in fact, so like in a perfect world, if we can perfectly observe the x's, we will just go and observe the x's. Okay, and then we don't need to do any estimation and so on. But reality is different. Some things are difficult or extremely difficult to measure directly, and then even if they are easy to measure directly, you will go and measure them. But basically, measuring does not tell you the exact thing, because there are always measurement errors. Okay, and these errors can be like there are several types of measurement errors and so on and so forth. Okay, now let's study expectation x minus x hat. Now, if you see something like this, okay, now if you see random variable, so there is x here, right? So there is an x here. And what is x hat? X hat is the estimator. Okay, so this is the estimator. And so x hat is a function of y. So in our expectation, we have an x and y. So if you see an expectation like this, no subscript, and then there are random variables inside, so it means it's an expectation with respect to every random variable inside the expectation. Okay, so if I write something like this, it means that you take expectation x and expectation with respect to the y. You take expectation with respect to every randomness that is there inside the expectation. And then now we know, basically that we can do things in two ways. Basically, we can, take expectation x given y, and then take the expectation with respect to y. Okay? And this comes from that you can take the joint distribution and you can write down the joint distribution of x and y as x given y multiplied by the distribution of y. And so you can focus initially on the conditional distribution given x. And so what is this thing? What is the inner expectation here? What is the expectation of x given y if we use the conditional expectation of x given y? So the first term will be expectation of x given y. Now, given y, this is a constant. So this is constant given y. So when you apply the expectation, because you are giving the expectation given y, then this will be a constant, and the expectation of a constant is the constant itself. And so the difference will be 0, and then the expectation of y of 0 is just equal to 0. So the expected value of x minus x hat is equal to 0. When we use x hat to be the expected value of x given y, okay? And so again, what we have from here is that the expected value of x is equal to the expected value of x hat, which is the estimator. And when we have an estimation technique that satisfies this relation, that the expected value of x is the expected value of the estimator of x, we say that the estimator is unbiased. Okay, so MMSE is an unbiased estimator. Okay, so again, when we find that x, the expected value of x is equal to the expected value of x hat, this is a property of estimators that that we call unbiased estimators, and we will encounter it later when we study like another technique for estimation. Okay, but for now, take it like as a matter of definition. Okay, let's do an example. Okay, so let's do an example for the easy case in which n is equal to big K is equal to 1. So we have basically, big N is equal to 1, big K is equal to 1. We have random variables x and y, and this is the distribution of x. So basically this thing here is like, it's a linear PDF and it's defined from 0 to 1, and then this actually is the distribution of y given x, okay, and it is given by this weird looking function. And now we want the expectation. So again, if I ask you what is the MMSE, so what is the MMSE of x given y? So again, this thing here, you do not need to reinvent the wheel. We know now the result of this problem, of this question. The answer to this question is known now, and you should use it directly later. It's basically the expectation of x given y. And to compute the expectation of x given y, well, you need the distribution of x given y. And so you start your problem by finding, okay, what is the distribution of x given y? So the distribution of x given y is the joint divided by the distribution of y, and the joint can be written in this way here to make use of what is given in the problem statement. So the joint, I can write it as the distribution of x multiplied by the distribution of y given x. We know these two guys from the problem statement. We know what is the PDF of x, and we know what is the PDF of y given x. Okay, and what about the PDF of y? Well, the PDF of y itself is the integral of the joint over x, right? And the joint can be written as f of y given x, f of x dx. Okay, and so basically in the denominator we just have the integral of the thing in the numerator. Okay, and so this will give us the distribution of y as a function of a small y. Okay, so you carry out the integrals, and as I say, typically integrals that you encounter here, you find that the polynomial thing, exponentials, and so on. and this is the distribution of x given y. And now the estimator is the expected value of x given y, and so what you do is that you apply the formula. So basically this is the integral, so x is living between 0 and 1 in this problem, and you take integral of x multiplied by f of x given y, x given y. This is the conditional expectation. It's you compute the expectation, but you use the conditional distribution, and you integrate with respect to x, and you end up with a function of y. Okay, and so you carry out the integration and you get this function, and so here is your MMSE. Okay, so so in other words, so what is this telling you? Now you have x and y, and they are basically, they have a joint distribution which can be basically obtained by multiplying these two guys together, the f of y given x multiplied by f of x. So they have a joint distribution. Now, if you go and observe y, you measure y, okay, so you have a measurement, you have a number right now. I will talk about this. So you go and measure y, and then you ask yourself, what is basically my best guess for x? Okay, what is the best guess? Again, best in what sense? In the sense of minimizing the mean squared error. Then you take your observation and you plug it in this function. 3 times y plus 1/2 over 4y plus 1. Okay, and then you get basically your MMSE estimate. Okay, so so basically MMSE estimation, like it's an exercise basically related to the previous chapter. So like you want to compute it, you know, basically you will need the conditional expectation, and if you want the conditional expectation, you want the conditional distribution. Okay, so this is, you know, where you spend your time to get these things, and then you compute expected x given y. If you wanted the minimum mean squared error averaged over y, then again the formula, the minimum mean squared error, is you obtain variance x given y, and then you take expectation given y. Again, it becomes an exercise in the old stuff. So to get variance x given y, what is variance x given y? So what is variance? Expectation of the random variable squared minus the expected value of the random variable, then squared. If you condition y, then you do everything conditioned on y, okay, which means that you use the distribution of x given y. So expectation of x squared given y, so you will integrate x squared, but you multiply by f of x given y, which was obtained earlier in the problem, and then you get this is the second moment given y. The variance is the second moment given y minus the first moment given y squared, and then you get something that depends on y. Then if you want the minimum MSE, again, here by minimum MSE we mean the minimum MSE averaged over y, so you just take this quantity, multiply by the PDF of y, okay, which was basically the denominator here, and you do the integration, okay, and here is what you get. Okay. Now, so this example tells you, so what do we need to find the MMSE estimate? And if you are further interested in obtaining the minimum mean squared error average over y, so we need things like this, right? So we need joint, right? So basically MMSE needs, we need this thing, okay, which is f of x1, xn, y1, yk, x1, xn, y1. So we need the joint, right? So this is what you need. And definitely in practice, in the overwhelming majority of situations, we have no idea what this joint is. Okay, so this is like a conceptual framework that is nice, but again, it's like, to compute this thing, if you want to compute it, right, then as if I don't give you the joint, you have no way to answer the problem. I mean, how can you obtain the expected value of x given y if you don't know the conditional distribution of x given y, which is something that you obtain from the joint? Okay, so you need the joint. Okay, you need the joint maybe directly, or the joint, you have the marginal of the x, and then you have f of y given x or something like this, but you need basically the joint. So in practice, of course, we don't have this thing here, so one way is actually to estimate it. So this is a big branch of statistics, which is how to estimate joint PDFs. Okay, so you may go and try to estimate this thing, and we don't study it in this course here. So again, it's a big topic, and how, if you don't know the distribution, how do we estimate it? Okay. But then if you know, another thing is that, okay, so someone asked here about machine learning. So in machine learning, we have not distribution, we have a training set. Okay, a training set. So basically we have XY pairs, many of these. So like we have, you know, we basically have those. So it's like we have measurements of the X's and the Y's obtained somehow. Okay, so again, this is how we construct the training sets. How do we obtain them? Again, this is a big story. But the idea here is that you try to do your estimation problem or classification problem, which in this course will appear under the title hypothesis testing. You do things using data, using training data. Okay, so this will be your next step if you want like to continue studying these stuff. So here we are, like this is like the theoretical thing. Now, I mean, I do not want like to give the to imply that MMSE is useless. In fact, there are situations in which you can make these joint things, and you can make very good guesses regarding them without a big effort. Okay, so I mean, this is not useless at all. But definitely it's of very limited applicability. Okay, typically in real life we will just have training data, and we will basically try to build we may try to build our estimator directly using the training data, or you may do things like in two steps, by first estimating the PDF or CDF, and then the joint one, and this is an extremely difficult task, by the way, and then you basically obtain your estimator. Okay, so again, this is the surface. There are lots of things to be said and to be done. For the purpose of this course, if you don't know the distribution, and it's very difficult, basically use something that is called the LMMSE, which is the linear minimum mean squared error estimation. And so the minimum mean squared error estimation, which it's basically, you say, so this is my vector of estimates. Okay, they look like this. So we have functions G1 and G2, and you say, for simplicity, I will make those functions, I will force them to be linear functions or affine functions, if you want to be exact. So that's the reason here we use linear. So basically, we would make these, some constant, times y1 plus a constant times y2, and so on. So of course, the best estimator in a minimum mean squared error sense may not be linear. Just go to the previous example. It was like something, a linear function of y divided by a linear function of y in our previous example. And generally, it's not a linear function. But you may say, well, I will force it to be linear. Okay, so if you force it to be linear, again, the derivation is in the notes. Now your estimate becomes this thing. Okay, so your estimate of x that minimizes the mean squared error, but here again we are constraining the functions to be affine, then it is basically the expected value of x, okay, plus a linear function of the observation. So you take the observations, you subtract the mean vector of the observations, okay, and then you multiply by this matrix here, which is Cxy Cyy inverse. So Cyy is basically the covariance matrix of the observation vector, okay, and Cxy is the cross covariance matrix. So it's a matrix that looks like this, okay. So you take vector x, and then you subtract, the means like this, x2, and then you multiply by the transpose of vector y. So this is y1, and then y2 minus expected y2, and so on. And basically, what you get when you do the matrix multiplication is that CXY element KL will be the covariance of XKYL. Will be covariance XK and YL. So some people say this is the cross covariance. So cross covariance means that you are computing the covariance between like two random variables, that are not in the same vector. So basically one of them is living X and the other is living in Y. So you have cross covariance XKYK. Okay, so this is CXY. So basically your estimate is a linear function of Y. So you have Y minus expected value of Y, you multiply by this matrix, and then you have the expected value. Now, if you look at what is needed actually to compute this estimate, we need expected value of X, we need expected value of Y, and then we need these matrices which involve the covariance. So here we need only first and second order statistics. You don't really need the joint PDF. So you need to estimate something. So if you don't know anything, you just need to go and estimate. But here we need to estimate basically the first moment of each of the random variables, and we need to obtain the covariance, right? The covariance of each Y, of the measurements, and the covariance between X and Y. Now, relatively speaking, those are much easier to estimate than the joint PDF between vector X and vector Y. Okay, so LMMSE basically you use it for simplicity, because your estimator is a linear function, or maybe actually you are forced to use it because sometimes, again, or many times actually, you don't know the joint distribution, and perhaps the best are the statistics, the first and second order statistics, which means first moments and covariances. And so you just go and estimate these, and then you can plug in basically in this formula for the LMMSE. Okay. The minimum mean squared error will be the trace of this matrix. Okay, CYX is the transpose of CXY, and trace, as I said on the on the first slide, it's the sum of elements on the main diagonal of the matrix, or the sum of eigenvalues. Now this expression here, which again you take it for granted, the derivation is optional, and you can basically start using this formula. Basically, in the case in which you have just one random variable in vector X and one in vector Y, then this LMSE becomes, so this CXY becomes the covariance of X and Y, and then CYY inverse becomes 1 over the variance of Y. Okay, so this is a simple formula if you just have X and Y, and the minimum MSE, which is this trace formula, which may look scary, but in the case in which big N is equal to big K is equal to 1, basically it is the variance of X minus the covariance of X and Y squared over the variance of Y. And again, you can use these directly if needed. Now, LMMSE typically, so it's not the optimal estimator in a mean squared error sense, again, because typically, if you go and solve the MMSE problem, your function is not linear. However, there is a class of random variables for which LMMSE is the same as MMSE. Okay, and so this is a class of jointly Gaussian random variables. Okay, so jointly Gaussian random variables, basically, if you go and compute the LMSE, it is the expectation of X given Y. For these guys, LMMSE is like MMSE. It's like you just, if you go and compute the, the difficult thing, which is expectation X given Y, you will get a function that is exactly this one, which is used for LMMSE. Again, this happens if vector X and vector Y are jointly Gaussian. And so this is a technical definition. I mean, this is not something that is arbitrary. Jointly Gaussian does not mean that each X and each Y is Gaussian, by the way. So what is the story of jointly Gaussian random variables? So this is actually the topic of the tutorial session this week. So the tutorial session this week is fully on this topic of jointly Gaussian random variables. Okay, an example. So so let's here take one random variable x. Okay, so basically we have x and then we have vector y1 and y2. So we estimate one single random variable, and then we have basically two observations, y1 and y2. And let's suppose that, you know, our first observation is x itself to be estimated, but it's noise. So remember, this is the thing I said, that, you know, sometimes the relation between x and y is this simple relation, that each y is simply, you know, an x plus, you know, what you can call measurement noise or measurement error. Okay, so let's suppose that x is, you know, y1 is a measurement of x, but it's noisy. So y1 is not x, right? It is x plus z1, and y2 is x plus z2, and let's just suppose that x and z2 are uncorrelated. Okay, so the guys are uncorrelated. And you know, basically the second, you know, the first and second order statistics, all the guys are zero mean. And so what is the expected value of y1? What is expected value of y1? Expected value of y1 is expected value of, by linearity of expectation, expected value of x plus expected value of z1 by the problem statement. This is 0, this is 0, so this is 0. Same story for y2. You are also given the information that variance x is p, variance z1 is v1, variance z2 is v2. You say, okay, so where are the covariances? So if they are not mentioned in the problem statement, so it means that you can compute them. So basically the information in the problem statement is enough for you so that you can compute the covariances and the other stuff that is needed so that you can obtain the LMMSE estimator. Okay, so remember the MMSE estimator, remember the it was CXY, CYY inverse, and then you have basically y minus expected y plus expected x. So the covariance matrix of the y, so we need the variances of the y's. Okay, so what is variance y1? So y1 is x plus z1, right? So x and z1, they are uncorrelated. Great, because this means that the variance of the sum is the sum of variances. Okay, so this is p plus v1 by the problem statement. What is the variance of y2? y2 is x plus z2. They are uncorrelated, so the covariance is 0. So the variance of x plus z2 is the variance of x plus the variance of z2. So this is p plus v2. Okay. Now what is CXY? CXY is basically the expectation. Again, the general case, it's x minus expected x multiplied by y minus expected y transpose. Okay, so in our case here, x is 0 mean, and so this is x, and then we have vector y, also the y's are 0 mean, and so we just have this thing will be vector y in a row form, so it will be y1 and y2 like this. And so the expectation will be expectation of x multiplied by y1, this one, and expectation of x multiplied by y2. Again, since these things are not directly mentioned in the problem statement, so it means that you can compute them. So how can we compute expectation x, y1? Well, expectation x and multiplied by y1, take y1 and basically write it down in terms of its, you know, expression. You know, put the expression of y1, which is x plus z1, right? And so this becomes expectation x squared plus expectation x and z1. Expectation x squared, because x is 0 mean, is the variance of x, which by the problem statement is p. And then expectation x z1, because x and z1 are uncorrelated, okay, then basically the expectation is of z1 x z1 is expectation x multiplied by expectation z1, right? So uncorrelated means that the covariance is 0, okay, and so if the covariance is 0, it means that the expectation of the product is the product of expectations, and so this is expectation x, expectation z1. Each one of those guys is 0, and so it's p plus 0, so that same story if you want the expectation of x, y2. Again, put y2 x plus z2, then we have expectation x squared, that the variance of x, which is p, because x is 0 mean, expectation of the product x and z2, they are uncorrelated, so the expectation is the product of expectations, each one is 0, and so this term is 0, and we are left with p. Now, for the covariance matrix, you need the variances. You know, we have two observations, so our covariance matrix basically is a 2 by 2 matrix. On the main diagonal, we have the variances, which we computed above, but then you need the covariance of y1 and y2. So what is the covariance of y1 and y2? Again, they are zero mean. So covariance is just the correlation. It is expectation y1 and y2. Basically, write down y1 and y2 using their expressions in the problem statement. y1 is x plus z1, y2 is x plus z2, and we have four terms when we multiply these two brackets together. So we have x squared, we have xz2, xz1, and z1, z2. Expectation x squared is the variance of x, which is p. Expectation xz2 and expectation xz1, we did them before, and both are equal to 0. Expectation z1 and z2, basically, again, they are uncorrelated. So the expectation is expectation z1 multiplied by expectation z2. They are zero mean random variables. So basically, this is 0. And the only survivor here will be the variance of x, which is equal to p. So matrix CYY is given by such. So this is the variance of y1. This is the variance of y2. This is the cross covariance y or the covariance of y1 and y2, and this is the covariance of y1 and y2. Okay. So as you can see, it's like you are committing LMMSE, but what you are actually doing, you are basically solving problems regarding the previous topics. Like you compute you compute variances, you compute covariances, and so on and so forth. So this is CYY, the expression for LMMSE. It has the inverse matrix. So you invert this matrix, you divide by the determinant. It's a 2 by 2 matrix. So you swap the elements on the main diagonal, and you basically invert the sign of the off diagonal elements. Okay, so this is CYY inverse. And then what is the expression for the LMMSE estimator? Because the mean values are equal, the mean values are to 0, then basically this is the simplified form. And CXY, this was like PP. And CYY inverse is basically this matrix here. And you just multiply. So you multiply this 2 by 2 matrix by this 2 by 1 vector. Okay, and then you multiply this 1 by 1 vector. So basically, the row vector BB can be written as, you can take B as a common factor, and this is 1, 1. And you multiply, and so basically this row vector multiplied by this column vector, it is 1 multiplied by this thing, plus 1 multiplied by this thing, and this is your result. It's a linear function. Okay, so basically, as you can see, we have a constant. Okay, so constant multiplied by y1 plus another constant multiplied by y2, okay, and those constants basically involve what we know about those random variables. So we have p, we have v1, and we have v2, and let's recall those things are the variances. So basically p is the variance of x, v1 is the variance of z1, and v2 is the variance of z2. So this is the LMMSE estimator. Okay, so let's, for fun, what if Z1 is equal to 0 almost surely? What if Z1 equals 0 almost surely? Okay, so what if the variance of Z1 is 0? Okay, so if, okay, so let's do this. So if variance of Z1 is equal to 0, then Z1 is equal to expected Z1 is equal to 0 almost surely. Okay, so what will be the estimator? Let's see what the estimator will be. Okay, so V1 is, okay, so variance, so this is V1. Okay, so V1 is 0, right? So this term will go away. V1 is 0, this one will go away, and so it will be BV2Y1 over, so V1 is 0, V1 is 0, right? And so BV2, so this is Y1. Makes sense, right? Makes sense if you think about it. So if basically your first observation, which is X plus Z1, if there is no really measurement error or measurement noise, if Z1 is 0 almost surely with probability 1, then actually your first observation is not a noisy version of X, it is X itself. So if your first observation is X itself, it makes sense that your best guess regarding X will be Y1 itself. x is y1. Okay, so this formula, like, sort of asymptotically, it makes sense. So if you can, play this game, what if v2 is 0 and so forth. Okay, so basically what we have is that, this is the special case. If v1 is 0, it means that basically we don't have the first measurement is not contaminated. It's pure, it's x itself, and so your estimate here will be y1. Just y1 is equal to x in that case. Okay. The minimum MSE, it has a formula. Okay, and so for the formula, it is basically variance x. So remember the formula for the minimum SSE. Basically, if big N is equal to 1, it is variance x minus cxy, cyy inverse, cyx. And in this case here again, you plug in those guys and do the boring calculations, and you will end up with this. So this is the minimum mean squared error. And as you can see from the formula of the minimum mean squared error, if v1 is equal to 0 or v2 is equal to 0, the minimum mean squared error will be 0, right? It will be 0 because in that case, if either v1 or v2 is equal to 0, it means that you have an uncontaminated observation of x, and then you can just use it as your estimate for x, and it will be a perfect estimate, meaning that the mean squared error will be equal to 0. Okay, so this is like to give you a flavor of LMMSE. So again, the problem, you have the formula. Basically, you spend most of your time here basically computing the things that enter into the formula for the LMMSE estimate and for basically the minimum mean squared error. Okay, so this is where you spend your time. And what are the things that you compute? Basically, means, variances, and and covariances like this. Okay, and you will find like more problems on MSE in homework 9. Okay, let's go now to another topic, moment generating function. The moment generating function is a function that after basically we will actually know why it's called the moment generating function, but for now it is the expectation. We have a random we have a real parameter t, so t belongs to r, and then we compute the expectation of tx. Okay, so the moment generating function of random variable x is expectation e to the tx. Okay, so remember versus what we did in the previous tutorial session, we have e to the I ux, so that was the characteristic function. So in the characteristic function, we used I, which is the square root of -1. Here we don't have I, we just use tx. Now, this moment generating, this expectation here, of course, this function is always greater than 0, right? So it is always greater than 0, and so the moment generating function is greater than or equal to 0. It's non-negative. Now, who says that basically this expectation will always be finite? No guarantees. Okay, so this is different from the characteristic function. Remember that we have this property for the characteristic functions, but we don't have this thing here. So basically, there is a domain for the moment generating function. So those are the values of t for which mx of t is a finite number. Okay. Now, the domain of the moment generating function is guaranteed to include t equals 0, right? Because what is m of x of 0? It is expectation of e to the 0x, and this thing is equal to 1. E to the 0 is 1. Expectation of 1 is 1. So for any random variable out there, the moment generating function at t equals 0 is 1. Okay, it's not, it does not require any further thinking. It is 1. But actually, there are nasty random variables for which, the moment generating function is finite only at t equals 0. So these exist, okay? So like the Cauchy random variable, for example. So basically, it is, if you put t equal any positive or negative number, this expectation explodes. It is only a finite number that is 1 at t equals 0. Okay, so the moment generating function, there is no guarantee that mx of t is finite for every t. It is finite over, it can be finite over all R. This can happen. We will see examples. But you know, you can have the other extreme case in which basically the moment generating function is finite only at t equals 0. And keep in mind, the moment generating function at 0 is equal to 1. And the same story for the characteristic function, because if you put x equals 0, if you put u equals 0 in the characteristic function, you always get 1. But then the characteristic function, it has this thing that basically this is for every u in R. The magnitude of the characteristic function is upper bounded by, is less than or equal to 1 for every u in R. But for the moment generating function, again, sometimes the domain is just the singleton containing 0. Okay. How do we compute the moment generating function? Well, lotus. I mean, what else? Lotus. So basically, if you have the exponential random variable, so if x is exponential lambda, and you want to compute the expectation of tx, what do? So basically, you take e to the x, you take the function, basically, and then you multiply by the PDF, and then you integrate from minus infinity to infinity. Now, the PDF itself here is defined from 0 to infinity, so our integral is from 0 to infinity, and then we are basically integrating here an exponential function. So note the following, that we are integrating lambda e to the x, and then x is multiplied by t minus lambda dx. Now, if parameter t in the moment generating function is equal to lambda, which is the parameter of the exponential random variable, what will happen? If t is equal to lambda, we have exponential 0, which is 1, and then you are integrating lambda, which is a constant from 0 to infinity, that's infinity, right? So if you put t equals lambda, basically this thing explodes to infinity. What if t is greater than lambda? If t is greater than lambda, then this is a growing exponential, and basically the integral will also be plus infinity, right? So for the exponential random variables, basically for the moment generating function to be finite, you need t to be strictly less than the parameter lambda of the exponential random variable. Okay, so this is, so basically the domain here of the function is less than from minus infinity. So basically the domain here is from minus infinity up to lambda not included, if you want this expectation to be a finite number. And then in that case, if you do the integral of an exponential function, you get lambda over lambda minus t. On Blackboard, you find a cheat sheet for distributions, and for the distributions that we'll use in this course, in exercises, in the exams, and so forth, you will find basically the moment generating function provided. So I provided the moment generating function of those guys that will appear to you in the exercises and in the exams. They are also available on Wikipedia. So if you go to the page of any random variable on Wikipedia, on the right, you will find that there is a table containing information about the random variable, the distribution, the CDF, first moment, variance, stuff like this, and also information about moment generating function, and the characteristic function. Okay, so you can take things from Wikipedia, or basically for our purposes, you can take it from the basically this page on Blackboard. Okay. What if your random variable is discrete? I mean, again, lotus. You are computing, by the end of the day, the moment generating function is just an expectation. Apply lotus. So the moment generating function is basically, but it will be a sum now, and you use the PMF. So it will be a summation over the possible values of big X e to the tx multiplied by the PMF of X, which is the probability that big X is equal to small x. So if our random variable is Bernoulli P, so it's 0 with probability 1 minus P and 1 with probability P, then actually we have two terms in this summation. So one of them will be e to the 0, and then 0 occurs with probability 1 minus P plus e to the t1, and this occurs with probability P. And so this is the moment generating function, 1 minus P plus P to the multiplied by e to the t, and no constraint on t, right? So this thing will always, for a finite t, this thing will be finite. So this is an example of a moment generating function that is finite for every r, right? For every t in r, basically this is guy is finite. So this is contrary to the exponential case. For the exponential case, you are only finite from minus infinity to basically to the parameter of the exponential random variable, which is lambda. If x is Poisson lambda, okay, so Poisson lambda, again, Lotus law, law of the unconscious statistician. So basically, you take e to the tx and you multiply by the PMF corresponding to the Poisson random variable. So the random variable big X is equal to small x with probability lambda to the power x over the factorial of x multiplied by e to the minus lambda, where lambda is a positive number. And then you basically do this, this summation. You can take this guy as an outside factor, and then you can combine lambda to the x e to the tx as lambda e to the tx over x factorial. And what is this thing? So it is very important, let me write it in red, to recall the Taylor series of the exponential function. The Taylor series of the exponential function is very important. It looks like this. Okay, so e to the z is summation n from 0 to infinity z to the n over the factorial of n. And so summation here from small x 0 to infinity factorial of x in the denominator. In the numerator we have lambda e to the t to the power x. So basically this is e to the this thing. So it is e to the lambda e to the t. Okay, and then we have e to the minus lambda outside, and so we can combine them. And so this is the moment generating function of a Poisson random variable. It is e to the lambda, and then in the exponent we have also e to the t minus 1. And again, basically it seems that this, because this is actually valid every z, for every z that is a complex number even, then actually there is no constraint on t. T can be anything, and so this is another example of a moment generating function basically that is finite basically for every real t. Okay, so moment generating function of ax plus p. You can write down this thing, e to the t atx e to the tb, right? So this is the nice thing about, e to the sum. Then you can split it like this. This is a constant, so it can be pulled outside, and then we are left with expectation e to the atx. So what is this thing? So this is expectation e to some number multiplied by x. So this is the moment generating function of x evaluated at this thing, which is 80. Okay, so basically the moment generating function of ax plus p, where a and b are constants, it's e to the tb, and then the moment generating function of x itself, but rather than mx of t, we have mx of a multiplied by t. Then now comes basically a motivation for the moment generating function, and it is something like for the characteristic function. Why is even this thing like nice or useful in some way? It's useful because the moment generating function of a sum of independent random variables is the product of moment generating functions. So you don't need to do convolutions. It is just the product. And to see this, what is the moment generating function of the sum? It's expectation if the sum is s e to the ts. So basically it is e to the tx1 plus tx2 plus tx3. Now if the guys are independent, okay, so again e to the tx1 plus tx2 and so on can be written as a product. So this is e to the tx1 multiplied by e to the tx2 multiplied by e to the tx3, and because the x's are independent, expectation of a product is a product of expectations. Okay, and so this is what we have because of independence. And then what is this thing? For xk, this is its moment generating function, m of t sub xk here. So again, you start with the moment generating function of a sum, and you end up with a product, much easier to handle, rather than doing convolutions and stuff like this. Okay, and the same story applies for the characteristic function. Now, let's use this actually to prove something regarding the Poisson random variables. Suppose that you have n Poisson random variables, each one with a different parameter, but they are independent. Okay. Now, suppose you want to know the distribution of the sum, and we have n of them. So imagine doing this using PMFs. I think it will be very complicated, but let's do it using the moment generating function. What is the moment generating function of the sum of Poisson random variables if they are independent? So if they are independent, we know that basically the moment generating function will be the product of the moment generating functions of each one of them. And so we go upstairs here. So basically the moment generating function of a Poisson random variable, it is e to the then we use the parameter of the Poisson random variable multiplied by e to the t minus 1. And so for xk, this will be lambda k e to the t minus 1. And so this product here is e to the lambda 1, e to the t minus 1 plus, it's multiplied. So let's put it like this, minus 1. Then it's e to the lambda 2, e to the t minus 1. So we have exponentials multiplied together. Then you can add the exponents. And so the lambdas will basically combine. And then you have e to the t minus 1. And so what is this thing? So the moment generating function of the sum, it looks like this: e to the t minus 1, e to the t minus 1, and then a positive constant here. This looks exactly like the moment generating function of a Poisson random variable. So basically the sum is Poisson. It is just that the parameter of the Poisson is the sum of the parameters of those guys here entering into the sum. Okay, yeah, we'll talk about how it's even called the moment generating function. Okay, so we will see it on the next slide. Okay, so basically if you have expectation e to the tx, okay, this is for a real parameter t. This is called the moment generating function. It may explode to infinity. It depends on what random variable we are talking about. For all random variables at t equals 0, this is equal to 1. We have other random, there are some random variables for which this expectation is finite for every t. In R, there is some random variables in which it is only finite at t equals 0. Moment generating function of a sum of independent random variables is a product. Okay, and so it gives you, again, it allows you to do manipulations of the sum in a much easier way than if you use something like the PMF or PDF in the case of continuous random variables. Okay, so now let's go to the case. On this slide, we'll basically talk about the sweet case for the moment generating function, but let's start by doing this. Suppose that I tell you that the moment generating function is finite at t1 and is finite at t2. So I give you two values of t, t1 less than t2, and I tell you, I computed the moment generating function at t1 and it is a finite number, and I computed the moment generating function at t2 and it is a finite number. Okay, then what can you conclude from this? The moment generating function will be finite at any point, at any value of t between t1 and t2. Moreover, the function, the moment generating function between t1 and t2 will be a convex function. Okay, so how can we prove something like this? Basically, it's the proof makes use of the convexity of the exponential function itself. Okay, so what we do, this is a reminder of what a convex function is. So we have a convex function on a set. The main definition of convexity is that if you evaluate so you choose 2 points in the set, eta and gamma, and then you choose a lambda between 0 and 1. The function is convex on some set big S, if and only if for every eta, for every gamma, and for every lambda between 0 and 1, g of lambda eta plus 1 minus lambda gamma is less than or equal to lambda g of eta plus 1 minus lambda g of gamma. Okay, so this is the main definition of convexity. And if your function is twice differentiable, then you know basically that you can check for convexity by computing the second derivative and checking whether the second derivative is greater than or equal to 0. If on S the second derivative is greater than or equal to 0, then the function is also convex. But the definition of convexity does not require differentiability. Basically, this is the main definition of convexity. Okay. So note this thing. This you need to have a good a view of what this thing lambda eta plus 1 minus lambda gamma. What is this thing? Or here in our case, we will take lambda t1 plus 1 minus lambda t2. So you have t1, you have t2. Lambda is a parameter from 0 to 1. So what is lambda t1 plus 1 minus lambda t2? It's a point between t1 and t2. Right? So lambda t1 plus 1 minus lambda t2 is a point between t1 and t2. If lambda is equal to 1, we are talking about T1. If lambda is equal to 0, we are talking about T2. If lambda is equal to 1/2, we are talking about the midpoint between T1 and T2. And generally, lambda T1 plus 1 minus lambda T2, again, it's a point on the line segment connecting T1 and T2. Okay, so this is this expression here, keep it in mind. So again, the exponential function is convex, and this function is differentiable. So if you differentiate it twice, you get something that is positive. So it is indeed a convex function. And so what's the convexity means that if you take if we take E and now fix an x, suppose that x is some fixed number, x, then lambda T1 plus 1 minus lambda T2, okay, this thing is less than or equal to, because of convexity, lambda e to the xt1 plus 1 minus lambda e to the x e to the xt2. Okay, so this is from convexity. Now take expectations of both sides. Okay, and if you take the expectations of both sides, okay, then here this will be basically the moment generating function evaluated of random variable x evaluated at lambda T1 plus 1 minus lambda T2. The right hand side, lambda is a constant, and if you take expectation of this thing, this is the moment generating function of x evaluated at T1, and 1 minus lambda is a constant, and the expectation of e to the T2x is the moment generating function of x evaluated at T2. Now, our premises are that basically this guy is finite, and this guy is finite. So a finite number multiplied by a number between 0 and 1 is finite. Same story here, and if you add two finite numbers, you get something that is finite. So this thing is always finite. Okay, so mx of t, where t is lambda T1 plus 1 minus lambda T2, this thing is always finite. So here is something nice again about the moment generating function. If I tell you that it is finite at T1, it is finite at T2, you are guaranteed to get a finite result if you try to evaluate the moment generating function at any point between T1 and T2. But you get more, because basically if you stare at this inequality, this is the definition of convexity. Okay, so basically, it means that between T1 and T2, the moment generating function is convex. And this piece of information may be important because later we will use the moment generating function in an optimization problem in something called the Chernoff bound. And so knowing that it is convex is good, right? Because convexity is relevant to optimization problems. Okay, so it is with this in mind, that the moment generating function, again, if it's finite at T1 and T2, it's finite at any point between them, and also it is a convex function. Now, let's talk about the sweet situation for the moment generating function. It's when t equals 0 is interior to the domain of the function, which means that, so this thing means that basically moment generating function is finite in a neighborhood of 0. Okay, so there is 0 here, and there is an open interval around 0 like this. You are guaranteed that the moment generating function is finite there. Okay, so question: what are the implications? Okay, so what are the implications if you compute the moment generating function, and around 0, and you find that it is finite here? Then first conclusion, which is basically the theorem, x are finite. This is, you are guaranteed that all, and here we are basically starting to establish sort of what is, why this expectation of e to the tx is called moment generating. Okay, so what has it, what is its relationship with the moments? Okay, so this is one thing, that if t is interior to the domain of the moment generating function, then all the moments are finite. Okay, so So suppose that basically the function, the moment generating function is finite on the interval from minus epsilon to epsilon, and epsilon is greater than 0. Okay, so this is given. And now take e to the epsilon x plus e to the minus epsilon x. Okay, then Taylor. So basically Taylor's expansion of the exponential is very important, and you will find that basically because of this minus sign, you will have minus 1 to the power k here, and so basically the odd terms in this summation cancel the odd terms in this summation, and you are left with double the even terms in in this first sum. Okay. Let k equals 2m, because now the indices are even, and so now this becomes summation m from 0 to infinity, and then replace each k by 2m. Okay, and so this is what till now everything is deterministic, and it is just the Taylor series of the exponential function. Okay. Note the following, that basically everything here is non-negative because we have epsilon to the power 2m, x to the power 2m. So even if x is a random variable that can be positive or negative, but here it is raised to the power 2m. So everything here is non-negative. And so basically this summation is definitely greater than or equal to one of its terms, right? So if you have a summation of non-negative terms, then the summation dominates is greater than or equal to one of its terms. So let's take its term v, okay? And so we have this inequality here, okay? Now, again, if till now, there is no really anything that is like random, and it is deterministic, and we made use of the Taylor series expansion of the exponential function. Now take expectation of both sides. So now say, okay, now take expectation of both sides. The expectation of this guy will give you mx of epsilon. The expectation of that guy will give you mx of minus epsilon. Remember, mx of t is the expectation of e to the tx. So the expectation of e to the epsilon x will be mx of epsilon. E to the minus epsilon x will be mx of minus epsilon. And this is lower bounded by 2. Epsilon is just a positive number, so expectation, it will remain as is. And then we have the expectation of basically x, it is squared, and so basically I can write it like this. Okay. Now, what do we know about the moment generating function? We know that this moment generating function is finite on this interval here, right? Because it is finite on a neighborhood of 0. So this guy is finite, and this guy is finite. So basically the moment of order EV is finite. Okay? But this is true for every v, right? Because like this is a sum of non-negative terms. It is greater than or equal to any of its terms. So this v is really generic. It can be any of the terms. So you can use, basically v can be 1, 2, 3, and so basically the moment can be, any moment of your choice. But those are even. But remember, we studied, in a previous lecture, that basically, let's say that the 100th moment is finite. Then every moment below 100 will be finite, including the odd ones, right? So basically, every moment will be finite. So if you wonder, where is expectation of x to the power, magnitude x to the power 1001? Is it finite? Is this thing finite? Well, expectation of magnitude x10002 is finite because all the even moments are finite. So this one will also be finite. Okay. So because of this relationship between the moments, then if you prove that all the even order moments are finite, then actually all the moments are finite. Okay. So this is very nice. If 0 is interior to the domain of the moment generating function, which means that the moment generating function is finite in a neighborhood of 0, you are guaranteed that all the moments of your random variable will be finite moments. Okay. There is more. You can now obtain the moments by differentiating the moment generating function In fact, the vth moment will be the vth derivative of the moment generating function evaluated at 0. And that's the reason it's called the moment generating function. You can obtain the moments of the random variable by simply differentiating this function and then setting the parameter t equal to 0. Okay, so let's see why this is the case. So the moment generating function, again, by definition, it is this expectation, and so it is expectation of summation k from 0 to infinity t to the kx to the k over the factorial of k, again, by the Taylor series expansion of the exponential random variable. And let's first investigate this expectation with t and x replaced by the absolute value. And so why are we doing so? We are doing so because we have expectation and we have an infinite sum, and we wonder if we can interchange the order of expectation and infinite sum. Okay, so Hoeffding gives you a sufficient condition. Okay, so we are basically checking Hoeffding. We are checking what will be the expectation of this sum if basically what we have are things that are non-negative. So t is replaced by absolute t and x is replaced by absolute x. Okay, so let's go do this like sort of a step on the side, on the margins, and see basically whether we can apply Hoeffding. If it's applicable, then we can actually take the expectation inside. Okay, so this is the Taylor series expansion of e to the basically absolute value of tx. Now, e to the absolute value of tx, well, basically tx can be positive or negative. Okay, so this thing is either e to the tx if tx is greater than or equal to 0, or it's e to the minus tx if tx is less than 0. So e to the absolute value of tx is upper bounded by the sum of these two guys, right? Because it is equal to one of these guys depending on whether tx is positive or negative. So e to the absolute value of tx is upper bounded by e to the tx plus e to the minus tx. But the first expectation, if you apply to this, it's the moment generating function at t, and the other one is the moment generating function at minus t. Okay, now if we are talking about basically values of t around 0 such that they are basically in the domain of the moment generating function where it is finite, then these two guys are finite, and this basically expectation of the sum of the absolute values will be finite. So now we can apply Hoeffding. So Hoeffding tells you that if you do this thing and it is finite, you can go back to your original problem and you can interchange the order of expectation and infinite summation. So we can bring the expectation to us. But again, for Hoeffding to work, again, we need the existence of a t and the minus t, such that basically at t and minus t, the moment generating function is finite. We need basically 0 to be interior to the domain of the moment generating function. If that is true, we can interchange. We can take the expectation to the inside, and now we can write the moment generating function as a series. It is basically summation t to the k, expectation x to the k over the factorial of k. And you know from your studies of calculus or real analysis or whatever that basically if you write down a function like this, it is an analytic function, it is infinitely differentiable, and basically the derivatives, the derivatives will be related to this expectation of x of k here. Okay, so in this case, actually, if you have a function that can be written as such, again, as a series like this, this function is actually infinitely differentiable over basically the domain wherever mx of t is finite, and so basically you compare this with the Taylor series expansion of the function. Okay, so just do a one-to-one comparison between this series and the Taylor series of the function, and you will get that the vth moment is basically the vth derivative of this function in our case here, if 0 is interior to the MGF, it is guaranteed that actually you would be able to differentiate the function. Actually, you can infinitely differentiate the function, and you differentiate it v times, put t equals 0, and you will get the vth moment of the random variable. Okay, so that's the moment generating function. Some people actually, when they use the moment generating function, they just restrict it to this case. Okay, so they just use the moment generating function in if this nice thing happens, in which the moment generating function basically its domain basically is some neighborhood of t equals 0. In that case, nice things happen. The moment generating function becomes infinitely differentiable. You can use its derivatives to obtain the moments. All the moments are finite, and so basically nice things happen. And again, you know, I need to emphasize, for example, that what I proved is not like in two ways. So, for example, you can have a random variable like the log normal random variable, and 0 is not interior. 0 is not interior to the domain of the moment generating function of a log normal random variable. However, the random variable have finite moments. Okay, so for example, if you go to like a problem, you know, is theorem like this, its converse is not necessarily true. So you can have random variables with finite moments, but whose moment generating functions are not nice. Okay, so basically they are not finite on a neighborhood about 0. Okay, but if this is the case, again, you get the moments are finite, it's guaranteed, and also you get this nice relationship between the moments of the moments and also the derivatives of the moment generating. So basically, the moment generating function, it is, you know, it can be used. If I give you mx of t, you can compute every moment by basically differentiating it and setting t equals 0. But you know, we know now it's not generally true. So this is the case when 0 is interior to the domain of the moment generating function. Okay. Now, Hoeffding lemma. So there is an inequality in probability called the Hoeffding inequality. Okay, and so we will talk about it later. But for now, it requires something called the Hoeffding lemma. Okay, and the Hoeffding lemma basically is an upper bound on the moment generating function of basically a random variable that lives between a negative a and a positive b almost surely. Okay, so here is the setup. So we have a random variable x between a and b. A is negative and b is positive, and x is 0 mean. Okay, and so again, so basically x is between a and b almost surely, and expected x is equal to 0, right? And this thing, it has a moment generating function. How do you compute the moment generating function? Well, give me the distribution. But I want to make a statement regarding random variables that are like this without going into specifics. So definitely we don't want, like, you know, again, for the moment generating function itself, we need to know what distribution we are talking about. So what we will do is that for all those guys, regardless of their distribution, we will have a nice upper bound on the moment generating function. Okay, and this will be useful later when we talk about the Chernoff bound. Okay, so why having this upper bound? It may seem like just an, you know, it is not just a theoretical exercise. It is basically used in the derivation of the Hoeffding inequality, which is like used a lot in, you know, in big data and machine learning and computer science, and so it has so many applications. Okay, so you can write down x. So x is between a and b almost surely. You can write, so we can write that x is equal to lambda a plus 1 minus lambda b, right, where lambda is between 0 and 1. So if lambda is 1, x is a. If lambda is 0, x is b. if lambda is 1/2, x is the midpoint between a and b, otherwise it is a point between a and b, right? Because we know that x is between a and b with probability 1, so we can express x as lambda a plus 1 minus lambda b. Okay, so this is x in terms of lambda a plus 1 minus lambda b, and lambda is between 0 and 1. Take expectations of both sides. Expected x is 0. I mean, this is the class of random variables we are talking about. They are 0 mean. And so the expectation a and b are just constants. A is negative, A is positive. So expectation x equals 0 is expectation lambda multiplied by a plus 1 minus expectation lambda multiplied by b. So now it is like a change of variables. We are basically, rather than working with x, we are working with lambda. And lambda is between 0 and 1, and the expectation of lambda from this equation here, again, you can solve for expectation of lambda, and it is equal to b minus a. It is equal to b over b minus a. Remember that a itself is a negative number. Okay, so this is basically b minus b over b plus the absolute value of a. Okay, now take e to the tx. Now write x is lambda a plus 1 minus lambda tb. Now exponential function is a convex function. That is great. So what does convexity means? It means that e to the, so again we have e to the lambda, and then we have ta plus 1 minus lambda tb. Okay, so this by convexity is less than lambda, the function applied to ta plus 1 minus lambda, the function applied to tb. Okay, so this is from convexity, the definition of convexity, and the exponential function is convex. Then take expectation of both sides, then we have the moment generating function of x, and then we have expectation of basically here, if you take the expectation of this thing, so basically you will get expectation lambda e to the ta plus 1 minus expectation lambda e to the tb, and then we have a formula for the expectation of lambda, so plug it in. And so this will be an upper bound on the moment generating function, but it is not very nice upper bound. We need more. So we will write this mx of t we will write the upper bound on mx of t in this form, e to the gt, right? You can take anything, if you know that this thing is non-negative. Is this thing non-negative? Is it non-negative? Yeah, you see a minus sign, but again it is deceiving because a itself is negative, and we have the expression, so this thing is non-negative. Okay, so again you see a minus sign, but remember that by definition a is a negative number, b is a positive number, so this thing is non-negative, so we can actually take its logarithm, and we can write down this thing as e to gt, where gt is the logarithm, right? So you have alpha is e to the ln alpha, right? So if you have this thing and you write it at e to the gt, then what is gt? It's the logarithm of this thing here. Okay, so gt will be the logarithm of this function. Okay, and then we will study function g. Okay, so function g, basically if you put t equals 0, it will give you, this will be 1, this will be 1, you will have ln b minus a over b minus a, that's ln 1, that's 0. Okay. Then you can differentiate it once, and you will find that its first derivative at 0 is 0. And then you can differentiate it twice with respect to t. Okay, again, this is like basically using the rules of differentiation, nothing else. And you will discover basically that this is its second derivative. Okay. And the second derivative is greater than or equal to 0, again because a is a negative number. In the second derivative, we will use the arithmetic mean geometric mean inequality. Okay, so we have two guys, so arithmetic mean geometric mean, okay, is that, so we have alpha beta are positive, then we know that alpha beta, basically square root alpha beta is less than or equal to alpha plus beta over 2. And so squaring, we have alpha beta is less than or equal to alpha plus beta over 2 squared. Okay? So the next lecture will basically continue. By studying, this second derivative of g of t. Okay, so again, the final thing to say here in this lecture, The big picture is that we are interested in having an upper bound on the moment generating function of a class of random variables. What are those random variables? Those are random variables that are zero mean, and they are between a negative and finite a, and the positive and finite b almost surely. Okay, and so what we will do is basically continue constructing this upper bound, and then later in the course we will use it to derive the Hoeffding